Body. Myself, Somi Mondal, a Prime Minister Research Fellow in the discipline of mathematics at IIT Madras. Today, this is my tutorial 3. In my this live session today, we are going to discuss about what to mean by differentiability of a multivariate functions. Okay, so at first I want to start with what is the tangent plane. In my lecture, uh, I want to fix our multivariate function as two variable functions only, and we can generalize this concept of for higher variable. Okay, so fixing that our function is two variable. Okay, so f domain of f in R2. Okay, this is function from D to R. Okay, so what do we mean by tangent plane? Okay, so what is the definition of tangent plane and what is the formula for tangent plane? Okay, okay, basically if we draw one picture, okay, this is your x, y, this is your z axis. Okay, and if we consider the surface S, okay, surface is z equal to f of xy, like this is your suppose one surface, whereas z equal to f of xy. Okay, and take one curve on this plane, sorry, take one curve on this surface. Okay, so and take one point P here. Okay, and draw one tangent line here. Okay, this is your tangent line. Now what is the tangent plane? Tangent plane to S. Okay, S is the surface of this one. The tangent plane to S at P is any point consists all possible tangent line and P to the curve C. This is your curve. Okay, to the curve C that lie on, which is lie on S and passes through the point P. Okay, so tangent plane is nothing but a collection of all possible tangent line at the point P to the curve C, which is lie on the surface S and which is the passing, this surface is also passing through the point P. Okay, this is a tangent plane. Then what is the equation of tangent plane? Okay, let S be the surface z equal to f of xy. Here we are fixing our function as a two variable functions. After that we can generalize this concept for higher variable also. Okay, where f of x, f of y, partial derivative with respect to x and partial derivative with respect to y are continuous on the region D. Okay, D is the domain of the functions. Okay, the equation of the tangent plane the equation of the tangent plane to S at a given point P. Okay, where P is A, B, C. Okay. This P is on your S. Okay. Is given by Z minus C equal to partial derivative with respect to x at the point AB into x minus a plus f of y AB partial derivative with respect to y at the point AB to y minus b. This is the equation of tangent plane to a surface z equal to f of xy at the point P ABC, which is on your the surface S. Okay, this is the equation of tangent plane for the two variable functions at a given point AB. Okay, ABC. Okay, so please solve one problem. Okay, question is find the equation of the tangent plane, okay, to the elliptic paraboloid, okay, z equal to 2x square plus y square at the point 1 1 3. So what is the question? You have to find the equation of tangent plane, okay, to the elliptic paraboloid z equal to 2x square plus y square. Okay, this is your surface S given by this function. Your f of xy z equal to f of xy equal to 2x square plus y, and here p is 1 1 3. Okay, so this is your equation of tangent plane z minus c, okay, equal to partial derivative with respect to x at the point AB into x minus a plus partial derivative with respect to y at the point AB to y minus b. So what is your z here? Z is this one. Okay, so z minus c is 3, okay, equal to partial derivative with respect to x at the point 1 1 3, x minus a is here 1, okay, partial derivative with respect to y at the point 1 1 3, y minus 1, b is here 1. Okay, so what we are getting, this is 4 x minus 1, this is 2, okay, at the point this one 1 minus 1. Okay, so if you do simplification, what will get? After simplification we will get 8 simplifies to z equal to 4x plus 2y minus 4 minus 2 minus 6 plus 3. What is minus 3? Okay, this is your equation of tangent plane to the surface elliptic paraboloid at the point 1 1 3. Okay, now we are going to discuss about what is the total derivative. Okay, before that we want to recall one thing. Recall that for a function if on one variable, okay, its differential is defined as how one defines for a single variable function, how it differentiable is defined as how d of f is nothing but f dash x is a derivative of the functions, okay, into dx for a single variable function. Everyone are familiar with this one. So my question is, what about for the two variable function, how df is defined for that case? Okay, so my question is, what is our questions? What about for two variable functions, how df looks like, or how df is defined for this case? Okay, so for a single variable function, our differentiable is defined as for a single variable function, our differentiable is defined as this one. Okay, so our next question is how df is defined for two variable functions. Before giving the answer of these questions, I want to state one theorem. What is this? Is the increment theorem. Okay, theorem name is increment theorem. So what the increment theorem says? Increment theorem says like that. Suppose one two variable function defined on a domain D, okay, and with extra assumption that partial derivative with respect to x means f of x and f of y, partial derivative with respect to y, both are continuous. Okay, then our given function is continuous on the domain D, and the total increment can be written as some interesting form. Okay, so let's write the this theorem. Okay, let your D be a region in R2, let the function f is defined from D to R have the some following property: have continuous first order partial derivatives, okay, on D. So what is the extra condition has this function? This function, the both partial derivative are continuous. This is the assumption on this function f. This gives us guarantee that them f of xy is continuous on D, and our total increment is written as some interesting form, and the total increment, what is our total increment? Del f is del x plus difference between this two term is called total different, okay, total increment at the point AB. This total increment can be written as such one interesting form: partial derivative with respect to x at the point AB into del x plus f of y del y plus epsilon 1 del x plus epsilon 2 del y, where these two real number epsilon 1 epsilon 2 where epsilon 1 tends to 0 and epsilon 2 tends to 0, as both del x tends to 0 and del y tends to 0. Okay, so increment theorem says that suppose our two variable function have continuous partial derivative, then the function itself a continuous function on the domain D, and the total increment has this form. Okay, total increment can be written as this form, where the real number epsilon 1 and epsilon 2, epsilon 1 depend on this increment del x and epsilon 2 is depend on the increment del y. Okay, and epsilon 1 tends to 0 when del x tends to 0, and epsilon 2 tends to 0 when del y tends to 0, means epsilon and epsilon 2 tends to 0 when the both increment del x tends to 0 and del y tends to 0. Okay, this is the increment theorem says. Okay, now what is the total derivative? Total differentiable is fine, I think. Total derivative, total differentiable, both are fine, no issue. Okay, DIFF ERENTIL. What is the total differentiable? Let one two variable function is defined on D, which is subset of R2 to R. Okay, this is a two variable functions, real valued function basically. Yeah, this is given. Okay, this is given. Okay, the differentiable of f, the differentiable of f also called the total differential, okay, is defined as the differentiable of f, or total differentiable of f is defined as del f equal to f of x comma y dx plus f x y dy. So from where we are getting this one? If you looks the form of total increment in the increment theorem, if you put del x means this increment equal to dx and this y equal to dy, okay, then you will get this one. Okay, so where dx, if you put dx equal to del x and dy equal to del y, are in the increments theorem. Okay, basically these two, this del x and this del y are the increment. Okay, and the increment in x and y respectively. Then del f is a linear approximation. Then del f is a linear approximation to the so what is the total differentiable? Total differentiable is nothing but a linear approximation to the total increment. Okay, so and this can be written as del f equal to partial derivative with respect to x at the point xy to dx plus f of xy into dy. Okay, so I am giving one example. Let's try to solve this problem. Basically this problem will observe how one can use the total differentiability, okay, or increment theorem. Okay, here we will use increment theorem as well as total differentiability. Okay, basically our df, this total differentiable, is a linear approximation to the total increment. Okay, we will use this concept in our next example or exercise. Okay, so this is given that you have one rectangle box. Okay, dimension of a rectangle box is measured to be 75 semi, 60 semi, 40 semi, and each measurement is correct to within 0.2 semi. This is given. You have one rectangle box. Okay, you have one rectangle box. Okay, and one side is 75 semi, another side is 60 semi, another side is 40 semi. This is given, and another things also is provided, that each measurement is correct within 0.2 semi. Okay, so the question is use differentiables, use differentials to estimate the largest possible error. Okay, when the volume of the box is calculated from this okay, what is given? You have one rectangle box which side is 75 semi, 60 semi and 40 semi, and each measurement is correct within 0.2 semi. So you have to use the differentials and you have to estimate the largest possible error. Okay, when the volume of the box is calculated from this measurement. Okay, in this measurement is correct within 0.2 semi. Then you have to find the largest possible error when the volume of the box is calculated from this measurement. Okay, so please tell me what is the formula for volume of a box? Suppose this is your x, this is y, and this height is z. Okay, the volume of the box, the volume of the box is v equal to xyz. Okay, so you have to use the differentiability of a three variable functions. Okay, so here this concept we can generalize for higher variable also. Here we have mentioned the total differentiability, total differential for two variable functions. This concept we can generalize for n variable function also. So here is the function f of function v is depend on three independent variable x, y, z. So this is three variable functions. So for three variable functions, what is the total differentiable? dv is nothing but the partial derivative of v with respect to x. Okay, dx and dv, dy and del v, del z, dz. Okay, so this is nothing but yz dx, xz dy plus xy dz. What is the provided? Provided is that the measurement is correct within 0.2. So increment, these things is given, this all the increment, this is in x, this is in y, increment in z, all are less than 0.2 semi. This is given. Okay, and we already know that total differentiable or differentiable is a linear approximate to the total increment. Okay, so your largest error in rectangle box is the largest error box is this is your v is approximate to since this total derivative and total increment related to that total increment, total differentiable is a linear approximation of total increment. Okay, so this equal to your this one, put the value of x, y, z and this increment. Okay, 14 to 0.2 plus 14 to 75, 0.2 plus 75, 60, 0.2. If you calculate, we will get this one. Okay, so the relative error is the relative error is 1980 divided by the total volume of the rectangle box, 75, 60, 40. Okay, this is approximate to 0.1, which is about to 1%. Okay, which is about 1%. Okay, so this is the largest error. So this is the largest error when the volume of the rectangular box is calculated from the measurement that measurement is given that each measurement is correct within 0.2. With this condition, the maximum error is up to about near about 1%. Okay. So we are now we are going to define. Now we are going to discuss about differentiability of a multivariable calculus. Till now we are familiar with what do you mean by differentiability of a single variable functions. Now we are going to discuss about differentiability of a multivariable functions. Here we are restricted ourselves for two variable functions, but this concept we can generalize for high variable also. Okay. So suppose you have one function is given. One function is given on a domain D, which is a subset of R2 to R. One two variable function is already given here. Okay, so this function f is called differentiable. Okay, f is called differential. Okay, at a point AB, which is in the domain D. Here we will see that differentiability of a function will depend on the increment, total increment of the function f. Okay, how it is related? Now we are going to discuss these things. F is called differentiable at a point AB on D if the total increment del f equal to b plus del y minus f of AB. This total increment in f with respect to increments del x del y in xy can be written as fx ab dx, del x. Okay, del y plus epsilon y del x plus epsilon 2 del y. Okay, where epsilon 1 tends to 0 and epsilon 2 tends to 0. Okay, as both del x tends to 0 and del y tends to 0. So one two variable function is given. So that function f is called differentiable at a point AB in the domain D if the total increment del f can be written as in this form. Okay. So that time we will say that function f is differentiable at a point AB in D. If you observe from increment theorem, suppose you have one functions f from D, the subset of R2 to R, such that fx, fy are continuous on T. Then by increment theorem, f is differential on T, not at a point. F is differentiable on the interior of D. Okay, we can write like that at AB, where AB is belongs to the domain D. Okay, so what is the f? F is nothing but f has the continuous partial derivative. Then by increment theorem, okay, then our this is our increment theorem. Then by increment theorem, what is the condition for increment theorem? Increment theorem, f has to be that all partial derivative are continuous, then our total increment is can be written as this form. This is the condition of differentiability of a functions. So using increment theorem, we can say that if we have one function such that the all partial derivative are continuous, then the function is differentiable at the point AB. Where AB is any point or interior of D. Okay, this is one observation. So one can ask, is there any other function which is that both the partial derivative are not continuous? Means can we relax one of these conditions? Okay, this is the strong condition that both the partial derivative are continuous. Can we relax this condition? So what is our question? Can we relax one of conditions? Can you relax one of the conditions? Condition means can you relax that both are partial derivative are not continuous or something else. Here we already assume the strong condition. Can you relax one of that one partial derivative is continuous, is another may or may not? So the answer is yes. Answer is yes. Okay. Answer is our yes. So what is the conditions? Condition is very simple. This is your f defined on D to R be such that both xy and both fx and fy exist. Okay, exist where? Exist on D, and at least one of them is continuous at AB. Then F is differentiable at the point AB. So from the increment theorem we can say that if one function has both partial derivative continuous, then F is differentiable at that point. The point is from the domain D. But one can relax these conditions. After relaxing condition, which type of functions are differentiable, we can generalize these things, but we can tell something, that some particular function which has both partial derivative exist and at least one of them is continuous at the point AB from the domain D, then we can say that F is differentiable at the point AB. Okay, in our previous observation we have seen that both are continuous, but here we are relaxing that condition. After relaxing the condition, this statement is like that: you have one functions on defined on a domain D, and both the partial derivative exist, and at least one of them is continuous. Then we can say that F is differentiable at the point AB, where that AB is from D, and one of the partial derivative is continuous at the point AB. Okay. Note it, I am not going for the proof, but one can prove that this is the similar result as the one variable functions. Okay. So if your function let f from D to R be differential at the point AB belongs to D, then F is continuous at AB. This is our normal expectation, because for one variable function we know that differentiability implies continuity, but converse may not be true for this case also. For two variable or multiple calculus, differentiability implies the continuity of the function, but converse is also may not be true for this case also. So I am not going for that example. Okay, so this is your exercise. What is your exercise? Find a example of function. Find a example of a function f such that f is continuous at some point AB from the domain. Okay, domain of f, but if is not differentiable at that point. Okay, this is your homework. Try to find one example of a functions. Okay. Now we'll discuss about directional derivative. Okay. Yeah. Before going to discuss about direction derivative, I want to recall what is the partial derivative of functions with respect to x and y. Okay. Yeah. Okay. So still I'm restricting myself for two variable functions. Okay. One surface is given here, z equal to f of xy. One surface is given here. I want to see what do you mean by f of x. What is this? What is the geometrical interpretation of the partial derivative of x with respect to xy at fixed one point a b, the domain D. Okay. So this is your x-axis, y-axis, this is your z-axis, and this is your surface. Okay, z equal to f of xy. We want to look what is the partial derivative of f with respect to x at the point AB. Okay, so from our previous lecture also we can see that. So this is your curve. Okay, z equal to, this is your surface z equal to f of x xy. Okay, and we are trying to observe what is the partial derivative of the function f with respect to x at the point AB. Okay, so when we are looking for the partial derivative of function with respect to x, we'll look for the intersect of the surface z equal to f of xy and the plane y equal to b will cut like that. This is your surface. Okay, and your plane will cut like this, and we'll get one curve on the surface. So we'll get one curve on the surface S, which is represented by z equal to f of xy, the functions. Okay, intersection of the surface and the plane y equal to b line. This is your curve C. So partial derivative with respect to x at the point AB is nothing but a tangent line at the point AB comma f of AB. It's fine. Now go to our okay, this is your y equal to b, this is your plane. Okay, sorry, not like that, this will be, I'm not going for these things. Okay, your z. Okay, so this is your surface z equal to f of x, this is your plane, this is your plane. Okay, this is your plane y equal to b. So here we are getting one curve C. C is nothing but the intersection of the surface S and y equal to b plane. So at the point AB, comma f of AB, this is the point P. Okay. So partial derivative with respect to x is nothing but a tangent line at the point P. Okay, this is your f of x at the point AB. Okay, it's fine. So here we can see that the f of x AB is a tangent line at the point P. So means f of x at the point AB is the rate of change in f is the rate of change in f with respect to change in x at the point AB. Okay, that is in the direction I. So partial derivative with respect to x at the point AB is the rate of change in f with respect to change in x at the point AB, that is in the direction, this rate of change is in the direction of I cap. Similarly, f of y partial derivative with respect to y at the point AB is the rate of change at the point AB in the direction j cap. So fx is the rate of change in the direction I cap, and fy at the point AB is the rate of change at the point AB in the direction j cap. Okay, so now our question is, how do we find the rate of change of f of xy at the given point AB in the direction of any unit vector, in the direction of any unit vector E cap. This is our question. So f of x is the rate of change in the direction I cap. This is unit vector. Okay, in the x-axis, and f of xy is the rate of change at the point AB in the direction of j cap. So our next question, how one can find the rate of change of f of xy at the point AB in any in the direction of any unit vector u cap. Okay, so for the reason this is the motivation of direction derivative. Okay, so derivative in the given direction, okay, given unit vector directions. Okay, so now I want to define what is the directional derivative. If on two variable functions from D is defined, okay, this is the defined on D, let x naught y naught is a integer point of D or point on D. The directional derivative of f of x comma y in the direction of a unit vector is given by equal to limit s tends to 0 f of x naught plus h a y naught plus h b minus f of x naught y naught, okay, divided by h, provided that this limit exists. Provided that this limit exists, okay. So this is the definition of direction derivative of a two variable function in the direction of a unit vector. This is given by this formula, okay. Limit h tends to 0 f of x naught plus h a comma y naught plus h b minus f of x naught y naught divided by, provided that this limit is exist, okay. So now I am giving one exercise, okay. Try to find the derivative, find the derivative of z equal to x square plus y square at 1 2 in the direction u cap equal to 1 by root 2 I plus 1 by root 2 j. This is your unit vector, okay. So you have to find the derivative of this given function at the point 1 2 in the direction of this one. So this is nothing but the direction derivative of this function in the direction of the unit vector, this one, okay. So your function is given by x square plus y square, okay. So what is the direction derivative of this functions f? At the point 1 2 is find the you have to find the limit s tends to 0 f of 1 is this coordinate 1 plus root 2 h 2 plus 1 root 2 h minus f of 1 2 divided by s. I am writing this formula only, nothing else, okay. Yeah, here x naught is 1, y naught is 2, okay, and a is 1 by root 2, b is 1 by root 2. I am putting the value of x naught, a, x naught, y naught, a and b in the this given formula. So now what we'll get, f of this one, so ultimately what we are getting, limit h tends to 0, 1 plus 1 by root 2 h square 2 plus 1 by root 2 h minus 1 2 means 5 divided by h. So what we are getting, limit h tends to 0, 1 plus 4 minus 5 is cancel out. So ultimately what we are getting, h square by 2, h square by 2 means h square plus 2 root 2 means root 2h plus 4 1 by root 2, 2 root 2. Okay. So what we are getting, from here we are getting 2 h by root 2, we are getting 2 root 2, sorry, we are getting 2 these things, okay, by h. So ultimately we are getting, what we are getting, we are getting 6 by root 2. Okay, this is your answer. So one can observe for these functions, okay, observation, that one function is this function is given by that x square plus y square, okay, and your u cap is defined by 1 by root 2 I cap, 1 by root 2 j cap, and the point is 1 2. So if you find this quantity at what is the, this is a plus comma 2 into 1 by root 2, what will get, this is nothing but 2, and this f4 at the point, this one is nothing but 4. So this and this one, this quantity and this quantity both are same. So one can rewrite this one is like that, f of x 1 comma 2, this is your this quantity, okay, write it as a ai plus bj, okay. So this is your a plus to b. So my next question is, so can we get some formula, or do you have any other formula except this limiting formula? This is limiting formula. Sometimes little bit, maybe a little bit difficult to calculate this quantity. So can we get, or do you have any simpler formula to calculate the direction derivative of a function at a given point and in some direction of some unit vector? My question is yes, but under some condition on the partial derivative of f. Okay, theorem is says that let f from D, which is subset of R2 to RB function, okay, be a function such that f of x, fx, fy are continuous on D, okay, then f of xy has a directional derivative at the point xy in any direction u cap equal to ai plus bj, and it is given by direction derivative of f at the point xy in the direction of the unit vector u is given by this formula. F of x at the point AB into A plus f of y at the point AB into B. So from the definition of definition of direction derivative in the limiting form, we can say that in any direction of some unit vector, the direction derivative of function may or may not exist. We can say anything from here that direction derivative of a function in any direction is exist. Okay, so there are maybe some functions whose direction derivative of some in some direction may not exist also, but this theorem gives the guarantee of existence of direction derivative of a function at a point in any direction, and explicitly we are getting one formula to evaluate the direction derivative of function at that point in the direction of some unit vector. Here we are not using the any limiting sense. Okay, so this formula is very handful to solve this type of problem. Okay, so what is the condition? Condition is nothing but that continuous partial derivatives. Okay, so you have one function such that the both partial derivative are continuous, then we can say that f of that two variable function, or you can extend this one for multiple function also, that function has a direction derivative at the given point in any direction of one unit vector. Okay, and it's given by this formula. So using this formula one can solve this one, this okay, so so using this theorem and using this formula one can evaluate what is the direction derivative of a function at a given point in any direction. Okay, u cap equal to this one. So please, I am giving one problem, please try to solve this one. So your function is given by this one. Okay, x cube minus 3xy plus 4y square. This is your function. So you have to find the direction derivative of this function. In which direction? Direction is given by the line direction of the line that makes an angle of pi by 6 with x-axis, okay, with x-axis. So you have to find the direction of derivative of this function. In which direction of the line that makes an angle pi by 6 with the x-axis, and take the any arbitrary point. Take which point? Take 1 point. At the point here you have to find the direction derivative of this given functions, okay. So at first you have to find the unit vector. This is your first step. So in which direction? The direction is nothing but the direction of the line that make an angle pi by 6, okay, with the x-axis, okay. So here the direction is given by the unit vector what is the unit vector? Is nothing but a cos pi by 6 I plus sin pi by 6. Is it or not? Please tell me. Yeah, because your the line makes an angle pi by 6 what with your x-axis, okay. So this is the obvious choice of unit vector, okay. So in this direction you have to find the direction derivative of this function at the point 1 1, okay. You have to find the direction derivative of the function at the point 1 1. So here if you look, that partial derivative of this function with respect to x and with respect to y both are continuous at the point 1 1. So we can use this theorem, okay, and we can use this formula also. A means this one is A, this is your B, this is your P, okay. What is f of x is at the point 1 1? F of x is so I am finding that f of x at the point 1 1 is nothing but 3x square, okay, minus 3y, okay, means 3. For y at the point y is nothing but minus 3 into y plus 4 into 2 into y, means 8 minus 5. So what we are getting? 3 into cos pi by 6 means root 3 by 2 plus this is 5, b is half. So this is your answer, okay. It's fine. Yeah, please let me know if you have any doubt or something. If you have any doubt, you can tell me right now, okay. Otherwise we can stop our live session here, okay. Okay then, bye bye, okay.
Hello?
Hello, please tell.
Sir, I didn't understand how could you take this unit vector in terms of sine and cos?
Okay, yeah, so I can explain you, no issue. So your what is given that you have to take in which direction you have to find the direction derivative in the direction of line, okay, that makes an angle pi by 6 with your x-axis. Is it or not?
Yes, sir.
Okay. So yeah, so you have to, at first you have to find you can find the equation of line also, or you can find the direction of line. Okay, what is this? So you have to find the equation line, this one, which the makes an angle pi by 6 with x-axis, is it?
Yes, sir.
Yeah. So what is the dy dx for this one? Your tan pi by 6, is it or not?
Yes, sir. Correct.
Yeah. So what is the equation of this function? Suppose this is passing through 0 0. Okay, so x, this one, it's fine.
Yes, sir.
Or if it's not passing through the point 0 0, then we'll get that y minus that point equal to this one into x minus that point. Okay,
Okay, sir. Got it.
yeah, you got it. So from here we can find this unit vector, this one, is it? It's
Thank you,
fine.
sir.
Okay, do you have any other question?
No, sir.